Alright, welcome everybody to Lab 1, Week 2. For this part of the lab, we are going to go through the actual, schematic portion of the lab. And talk through it and explain what we're doing and why we're doing it that way. If you've got questions while we're going along, stop me, ask them, I'll answer them. Alright, I'm going to create a new project, so I'm going to click on the New Project wizard. And as I've done this before, I'm going to click Use Existing Project Settings. If you haven't done it before, then just follow my video on setting up a new project. So I'm just going to copy all the settings from this project here. And hit OK. Yes, I want to remove all the I/O assignments. And I want to change the working directory. New folder. Lab 1, 26, 22, 1200. Right? Yep. Okay. And again, we'll just call this Lab 1. Apparently, copying my settings didn't bring over all the settings I wanted it to, so we're just going to go ahead and put it in manually here. 10M50DAF. (484C7). I'm going to leave that as none. I have a guide almost finished on how to set this up later, so for now, I'll leave it as none. Finish. Alright. To make a new schematic, I'm going to go File, New, and choose Block Diagram Schematic File. And then I'll zoom in here to show you, so you can see on the screen what's happening. Alright. So first, let me just pull up the book here and explain a little bit about multiplexer logic. If you've seen my previous video on multiplexer logic, then this should be reviewed. Essentially, this is what the book gives us, is a 2-to-1 multiplexer circuit. And if we follow the logic, we can see basically when S is on, then S over here is off, which means that this AND gate never passes. If that AND gate never passes, the only thing we get is this S2 on the other side. And if S is off, then this AND gate never passes, and then what we get is X1 on this side. And that's how we do a switch between two inputs. To expand on that, we're going to basically just say we're going to have, instead of a 1-bit input, we're going to have a 2-bit input, or 2 select pins. And that will give us 4 inputs. And as you expand your select pins, you get 2 to the N number, or 2 to the S for select pins, number of inputs. It just continues to grow. So we want a 4 input, so coming back to quartus, we want a 4 input. So we're going to start by laying down our AND gates. These are going to be 3 input AND gates. And previously I had showed others how to use the bus syntax, and it seemed to be causing more problems than it was solving. The syntax was a little confusing, and so that we can get through this lab and not cause more problems and time, we're going to do it just with wires. We're not going to worry about the bus syntax, and if you know how to use it, if you understood the previous examples I showed, great, and if not, I'll try and explain it again in a future lab. But for now, to get us through this one, let's just go with the simple wire setup. We're going to need 8 of these AND gates, because with wires we're going to treat each bit as a separate signal. So A0 and A1 will have their own signal, B0 and B1 will have their own independent signal. So we'll need 8 of these AND gates. Okay. We are going to need 2 4-wide OR gates, one for F0 and one for F1. So we'll do OR 4. Okay. We are going to need 2 inverters, one for I0 and one for I1, because we need to be able to invert both of those select pins. So I'll choose a NOT gate for that. Okay. We are going to need 6 inputs, 2 for I's, 2 for A's, and 2 for B's. So under Pin Tool, next to the Symbol tool, I'm going to click the drop down, and I'm going to click on Input. In fact, let's see, I might be able to do a spotlight on my cursor. So if I, yeah, right there, that's what I'm clicking on. So let's go to Input and do, let's see, 1. Try to line these up as best I can. 2, 3, 4, 5, 6. And I'll name those in a moment. The next thing we're going to do is, again, clicking on that. We're going to go to Output, and we'll need 2 outputs, 1 for each of the OR gates. Okay. Now, the thing that I want to emphasize, well, actually, first of all, let me go ahead and name these. And the thing I want to emphasize as I'm naming these is that my inputs I will be using later, so I will need to be able to name them something that's easily recognizable, because when I go to program my board, it's going to ask me how I want to assign those inputs and outputs. The other thing I want to emphasize as we go through this, I'm going to make this I0, is that these are my naming conventions. You don't have to follow them. You just need something that works for you. And also that when 2 nodes have the same name in this software, whether they are physically connected or not, as far as the software is concerned, they are connected. And that's going to make designing this a lot easier and a lot less messy. So then over here on my outputs, I'm going to call this F0 and F1. Okay. Now, the next thing I'm going to do as part of my setup is I'm going to start extending these pins on these AND gates so that they have nodes attached to them. So I'm clicking on, so I didn't show you that, I'm clicking on this orthogonal node tool here. It's the thin square line. And for each of the inputs and outputs, I'm just going to, sorry about that delay. Okay, so we're using this orthogonal node tool here, thin line, and we're just extending out, giving these guys some nodes. And I'm trying to make them slightly different lengths so that it's easier to read. On my machine, it's a little bit hard to read these as I start to label them. That's all I'm doing right now. I'll start labeling these in a second. If you get these little like right angles, if you're not paying attention, I'd suggest trimming them off, these little right angles, because it's really easy to accidentally connect wires in this program. And that'll mess up your design if you don't notice it and fix it. I'm going to do the same thing with these OR gates. And I'm just going to pass the output of this OR gate directly into its output pin. Oop. Alright, and with the NOT gate, I'll do the same. Alright, and we're done with the setup. So now it's mostly just a matter of labeling. So for the NOT gates on the left side, I'm going to call this, I'm going to right click and choose properties, and I'm going to call this name I0, and I'm going to right click on this one, properties, on the left side I'm going to call this one I1, and as I mentioned before, that has now physically connected I0 and I1 to the NOT gates, even though you can't see it. Because they have the same node, they are now physically connected. And I'm going to give this one a name, and I'm going to call this one NI0 for not I0. And on this right one, I'm going to call this NI1 for not I1, so that I can reference it when I need to. Okay. Now, I'm going to look through my instructions in the lab manual and find out which instructions I need to implement. So let's go ahead and open up my lab manual. And I have here that when I is 0, 0, then I need an ANDing of A and B. So F1 is A1 and B1, and F0 is A0 and B0. So let's go ahead and create an ANDing. So we'll need two input AND gates, one for A0 and one for A0 B0 and one for A1 B1. So and 2. So all I'm doing now is I'm creating the logic that we will eventually connect into our multiplexer. So I'm going to create 2 of these. And then the next one, I believe, is an O-ring. I'm going to pull this up and find out. This is, yep, A1 or B1 and A0 or B0. So I will change my symbol tool to be an OR gate. Choose OR2 for a 2 input OR gate. Oh. Yeah, that's fine. Okay. And then I will, next one I think is an equality operator. And if we search for XNOR in your book, I believe it will give us a truth table that we can look at. Maybe not. But let's think about a negation of XOR. So if we look at an XOR truth table, then we know that XOR is only true when X and Y are different. So if we negated that, it would be only true when X and Y are the same. So for an equality check, we'll use XNOR as the gate. Quartus, that's what I'm looking for. Okay, so we'll go to our symbols and we'll type XNOR. And we'll need 2 XNOR gates. Okay, and then the last one is the complement of A. That's easy. We can just do a NOT gate here and have 2 NOT gates. So these are the gates that we'll need for the logic for the various inputs that we're going to put into our multiplexer. And just as we did before, we're going to add nodes to all of these to expand them so we can label them. Cool. And then I'll go back to the arrow tool and start to label these. So I will call this one A0. And I will call this one B0. And for the output, well, this is going to be the input to the multiplexer when I is 0 and B, or when I is 0, 0, right? So this will be the F0 portion of the multiplexer specifically, because the output of the multiplexer is going to be 2 bits. So you're going to have F0 and F1. So this will be the F0 portion when the instruction I is 0, 0. So because of that, I'm just going to label this I00, F0. I'll say that's my instruction, I00, F0. That's what goes into F0 when I is 0, 0. However you want to think about that, that's my naming convention. Again, you can name it something that makes sense to you. It doesn't have to be this if you don't like this. The inputs on this side, I'm going to name it. These have to be named whatever your pin names are. So I say I'm going to name it, but its name is going to be whatever the pin names are. The outputs you can name whatever you want, so long as you're consistent. The inputs have to be named whatever you named your pins. So this one is A1. This one is B1. And again, just to reiterate probably the third time, the reason why that is the case is because these are my inputs, A0, A1, B0, B1. So when I name these the same thing, they become physically connected. Okay, so my output over here, I'm going to name, per my naming convention, I00, F1. Because this will be the F1 when I is 0, 0. So for the OR, we want, again, we want A0 or B0. And my naming convention, I'm going to name this I01 F0. And then this one I'm going to call A1, and this one I'm going to call B1, and my output I'm going to call I1B1. Or nope, I01F1. There we go. I01F1 for my naming convention. That's what I'm going to call this. Alright. XNOR again. This is going to be A0 equals B0. I think that's what the lab says. Let me double check on that. But for the third input, it is an equality check corresponding to the bits. So if A0 is equal to B0, F0 is equal to 1. So yes, that's what we want. So back to quartus. A0, B0. And this guy I'm going to call I10, F0. Same thing here, except this is going to be A1, B1. So A1 on this one, and B1 on this one. And on the output, I'm going to call this I10, F1. Because this is the output when I is 1, 0, and it's going to be the F1 portion of that. Okay, next we have properties. This one has to be a 0 for the negation. For the complement, it means the same thing. And that's A1. And then the output here, this, according to my convention, will be I11 F0, and I11F1. Great. So I have my values that need to be fed into my multiplexer. So if we go back to the book real quick, just to reiterate where this is all coming from, if I go back to page 62, I believe, we're going to go jump down to page 62. Okay, just to reiterate where all this is coming from, our x values are the same thing as these guys here. I've named them differently. I could have named them x1, x2, x3, x4, whatever. I named them something so it's a little easier for me to remember where everything goes. But these are going to be fed into an input of our AND gate. So, over here on this input here, this one is going to be this one's going to be A0. This one is going to be oh no, I'm sorry, not A0. Let me go back. This one is going to be I0 because it's the selection inputs that we're going to AND together. This one's going to be I1, or these need to be the negated portion, huh? They need to be NI1 and NI0. Because we want the, hold on, let's go back to features properties. We want this to be the first instruction, so this is going to be NI1. And then this is going to be I00F0. And then over here, this is going to be NI1. This is going to be NI0. And this one is going to be I00F1. Okay. This one is going to be N1 or NI1 for one of them, and it's going to be I0 for the other. This will correspond to 0, 1, the second possibility. And then this third one here is going to be I01 F0. And this one will be I0. This one will be NI1. And it doesn't matter which pin you put them on, they're all going into an AND gate. So if, for example, you put NI1 first on one of them for some reason because you just did, like I did, that's okay. It's all going into an AND gate anyways. And then this third pin is going to be I01 F1. Great. And we'll continue. This one is going to be NI0, because now we want the 1, 0 selected. So when I is 1, 0, so this is NI0. This one is NI1. And this last one will be I10 F00 so F0 is 1 0, right? Yep. Make sure that's how I named it. So that's how I named it. If you're not sure, you can always go back and check. Crossword is here. We're going to go N0. And 1. And oh shoot, no. Hold on. Okay, so we just did I0 and I0. No, I0 and I1. I0 and I1. So this one has to be 1, 1. We got 0, 0, 0. We got 0, 0, 1. We got 1, 0. So it's 1, 1, but I'm missing something. All is 6. So let me go back to the here and we'll check. So 0, 0, 0. And 0, 0, 0. I've got 0, 1, 1. I've got 0, 0, 1. And 0, 0, 1. And I've got, yeah, okay. Okay. I got a little bit off. So this needs to be an I0, which is correct. But then this one needs to be just regular I1, not. Otherwise, the 2 and will drive 0, 0 as the selection, and we'll get errors. Everything on its own unique combination of eyes in order for a multi-work. So we have N I0, then over here, we want I1. This is 1, 0. And then over here, we want I1, 0, okay. Hopefully that didn't look too much. Good. Just gotta make sure that all inputs are correct so that it matches this. Alright, now we're on to I0 and I1. Okay, that's 1. And we want I1, 0. Okay. And then here, we want I0. And I1. And I11 F1. Great. So these are now connected, and now we just need to pipe these into our OR gates. So I'm just going to label these guys so that I can easily type them in. I'm going to label this one F0. I'll call this because I already used the I00 portion, so we need to call this something that I can remember. This is for F0, and it's the first instruction. So I'm going to call this F01. Again, you don't have to use these if you don't like them. It's just a naming convention. And I admit this one might be a little confusing, but this note here is for F1, so this one's going to be F01. You just can't name a node with a number at the front, so that's one rule. It has to start with an alpha character. This one is going to be F10. This one's going to be hold on. This one's actually F. Oh, hold on. I messed this up. So this is actually F1 instruction 1. That's how I'm doing it. So this is F0 instruction 1, F1 instruction 1. So this is going to be F0 instruction 2, and this one's going to be F1 instruction 2. Then this is F0 instruction 3. This is F1 instruction 3. And this is F0 instruction 4. And this is F1 instruction 4. It's a little bit of an odd naming convention, I'll admit. I probably would do something different if I were going to do this again, but it works for our purposes, so I'll keep it. So now I just have to pipe all of these in. So this is going to be F01. This one is going to be F02. This one F03, and this one F04. And why are these all just the F0s? Because the output is going to F0. So we either have F0 instruction 1, F0 instruction 2, F0 instruction 3, or F0 instruction 4. And then on here we're going to have the same thing, except for it's just going to be F1 instruction 1, or F1 instruction 2, or F1 instruction 3, or F1 instruction 4. Okay. And now everything is connected, and the logic looks correct to me. So I'm going to go ahead and compile it. Yes, I want to save it. It has to be named the same thing as my project. You have to always have one file that has the same name as your project. If you don't, it won't work. And it's usually the file that it's usually your top level file, the one that you're going to compile. So if you didn't see what I clicked on to get there, it's that button right there. Usually it's a blue play button. Right now it's gray because it's compiling. Just takes a couple minutes, depending on the speed of your computer. Okay, now compiled correctly. That doesn't mean my logic is correct, but it means that I don't have any syntax errors, nothing is connected in a way that it won't work. So that's your first line of defense, is those compilers. But it tells you nothing about your logic. To test your logic, you need to write a test bench, which we will go over in the next lab. Okay, and one thing I like to do after the compilation is to go to Tools and look at the RTL viewer, because this I kind of consider my second line of defense. If it's a simple enough circuit, I should be able to kind of look at this view and see if it seems logically correct. So I'm going to look at my I0 and I say, okay, so here's not I0 and here's not I1, and in there we're getting A1 and B1 into this OR gate. So that looks right. And then same thing here, I could look and say this is not I1, but for some reason we're getting two inputs of not I1 into this, which seems odd. Not sure why we'd have that. So maybe that's something to look at. Maybe that's something that's not quite right. It shouldn't necessarily cause a problem, because not I1 and not I1 is still not I1, but it is strange, so that's worth looking into. To figure that out, I can go and see this is my first inst. So let's double click on that and click locate node in design file. That's this guy here. So this is AND gate here. It's not I1 and not I1. Yeah, so that's an error. I'm gonna mess that up. Oh, whoa, that was an accident. View, fit in window, and then let's zoom in from there. Okay. But yeah, so not I1 and not I1. That's definitely not what I want. This should be not I0 here. So if you see anything in the RTL viewer that strikes you as off, like I just did, you can go back and say, whoa, where I screw up. I'm going to go ahead and save that and recompile. So let's go now and look at our RTL viewer again. Netlist viewers, RTL viewer. And this should now have not I0, but now it has, oh yeah, right here. Okay, so inst was the one we were looking at, has not I0 and not I1. So this is now correct. And it is piping in as its input A0 and B0. So that's correct. And we can go through all these and verify that they're all correct. I will leave that as an exercise for you to do later. For now, I'm going to go ahead and close this. And I'm going to go to Assignments and choose Pin Planner. You can also click on this guy right here. Nope, sorry, not that guy. This guy. The one with the little, like, pin and pencil. But that's why I always just go here, because I can't ever remember what they look like. Alright, so in the Pin Planner, to get to this weird looking screen, and we're not going to really worry about this. It's like a graphical way to assign things, but it doesn't make any sense to anyone. So instead, we're going to look at our inputs, and we're going to look at the locations, and we are going to decide how we want to map these. So I want I0 to be, for my setup, and I did this wrong last lab, so hopefully I can get it right this time. I want I0 to be my far left pin, closest to the 7-segment display, and I want I1 to be my far right, or not my far right pin, the one next to it. So the one next to the far left pin, that would be switch 9 and switch 8. That's what I want. You guys can choose whatever switches you want, but that's how I like to do it. So to do that, I have to look at, not this, but I have to look at the user manual, DE10 Lite user manual. If you don't have this downloaded, it's on the Lab 1 page on Canvas, and you will want to download it. You will want to have a copy of it, because you're going to need to reference it for every lab. Alright, I've already got this on page 27. It's the correct page for the switches. If you don't have it, you can hit Control F and type switch, and just keep Control F-ing until you get to this yellow table. So this yellow table tells me, basically, for SW9, which is how it's labeled on the board, it tells me what the FPGA pin number is. And so for SW9, which is the far left one closest to the 7-segment, I'm going to use pin F15. So I come back to Quartus Assignment Editor. For I0 is the one I want. I'm going to use pin F15. And then I want I1 to be the one next to it. And so I'm going to go back to there, and I'm going to choose pin B14. Alright, now my outputs, we'll worry about that in a minute. I'm going to go now to A0, which I want to be, well, if I'm following my conventions, then let's think about this. So does it make more sense for I0 to be the one on the left or the one on the right? I0 is the rightmost in the vector, so maybe it makes more sense to swap these. It's important that you know how you've mapped your pins, because when you go to test it on the board and things don't work right, if you've got the wrong pins, that's the first place to look. So did I map my pins correctly? So in that case, let's let I1 be the far left one, and let's let I0 be the one next to it. And this was the mistake I made last time, so that when I was trying to test it, it wasn't making sense, and it was just because I had mapped my pins in a way that when I was testing it seemed counterintuitive. Alright, so now I'm going to go to A0, and that one then should be the rightmost pin, because I'm going to go ahead and switch now. I'm going to go all the way to the right of my switches to try and keep my I's and my A's and B's as separate as I can. So I'm going to let A0 be my farthest right switch. So let's go back to this. And my farthest right switch is pin C10. And then the next one to the left will be C11, and then we go D12 and C12. So C11, great, so that'll be the two right pins, and then I'll make the pins next to it be B0 and B1. So this is pin D12 and pin C12. If I remember correctly. Yep. 2 is D12, 3 is C12. Great. So now I want my outputs to just be 2 LED lights. So I'm going to scroll down here where it says user defined LEDs. It's just the next page. And I'm going to let F0 be the rightmost LED and F1 be the one next to it. So that's A8 and A9. Not sign editor. Pin planner. So F0, the rightmost LED, is pin A8, and F1 is the one next to it. A9. Alright, and I like those pin assignments, I think. And so I'm going to now go ahead and just hit close. There's no save option in here. Although I do want to show you quickly one very useful thing. So after you've made this, you're going to go ahead and hit File, and you can actually export these as a CSV file, so that when you're at home and you want to test or something, you can just have a CSV file and you can import it, so you don't have to go through this mapping again. So if I export that, it'll let me save that as a CSV file, and I'll call it something like Lab1 pin assignments. Something like that. And then to import them, you would go assignments, import assignments, and then browse for that CSV file. Okay? Great. So now that that's been done and I've made my assignments, I have to compile a second time. I have to compile once so that the pin planner knows about my ports, and I have to compile a second time so that my programmer knows about my assignments. It's kind of a silly thing. I don't know why. You would think that they'd be able to figure out the ports without a compilation, but apparently not. So. Alright, and then I'm going to go to Tools, and I'm going to click on Programmer. Alright, most of you probably will have this say no hardware. You go to Hardware Setup, and if it says no hardware, you're going to click USB Blaster. Now some have run into a problem where this option wasn't here. If you run into that problem while you're doing this, there's an easy solution. You're going to click on the File Explorer down here, just like your file browser. You're going to go to your C drive, which is, if you didn't change the default location, that's the install directory for Quartus. You're going to go to Intel FPGA Lite, where you've installed it. 21.1 is the only option you should have because you don't have multiple versions of Quartus installed. and then you'll click on quartus, and you'll click on drivers, and you'll run this. When you run that, it should say that USB Blaster was installed successfully, and then it'll have a couple of failures. The failures are okay, so long as USB Blaster installed successfully. Then close this, go back into hardware setup, and it should show up. You will also need to have your board plugged in for it to show up. So if you're not seeing it, also make sure that your board's plugged in. So that was one problem that other people were having in the labs previously. Another problem that some people were having was that after compiling, the board wouldn't flash correctly. It kept saying failed. If that happens, you have this SOF file here. Double click there, go to output files, and delete the SOF file. And if you have multiple ones, delete all of the SOF files. So we would just right click on that and choose delete, and then close this and close this and recompile. And that'll create a new SOF file with the new assignment, so that's like a hard refresh basically if for some reason the SOF file didn't update correctly and it's now failing. That was problem 2 that people in the labs were having. So I'm going to run through this compilation again. Okay, I'm going to click on Tools. I'm going to go back to Programmer. Make sure USB device is still USB Blaster. Make sure that my output file is lab1 SOF. Go ahead and click Program and Configure if it's not selected. And then finally, click Start. 100% successful. That's what you want to see. The easiest way, and most of the time it's already set up correctly, you should be able to just go in here, click Hardware Setup, and click Start. You shouldn't have to delete the file, recreate it, all of those steps. So they're just in case for some reason the setup didn't work the first time. So now let's see if my values pass. So 0, 0 should be when A0 and B0 are the same thing. So, or both 1 because it's an AND gate. So it's not the same thing. It's if A0 is 1 and B0 is 1, then I get my light turn on. And I'll show that to the camera as well. So I get my LED light when I've selected my switches correctly. Okay. And I'll flip the switches now on the far left. These are my high pins. So if I do 0, 1, that should be an OR gate. So that would mean A0 or B0 seems to work, or A1 or B1 seems to work. So just go through all of your options, make sure that they all work correctly, and if they do, then you're done. So that's it. That's the first part of Lab 1, and then for the second and third part, you're just going to do the same thing using Verilog instead of the PDF file. And I have a Verilog that takes you through the creation of a multiplexer. It doesn't take you through the entire lab, but it takes you through the creation of a multiplexer in Verilog. You can continue following along and expanding on that if you feel like you know how. I will expand on it probably next week as we continue through this lab. But I need to get people through the schematic portion first.
But it's making like Verilog for
Yeah, we're just literally making Verilog of the exact same circuit we just built here. And if you want to see, I'm not sure what Verilog will be created, but we can go to File and choose Create/Update and do a Create Verilog or create HDL design file from current file, and we can choose Verilog HDL, and we will want to call it something other than lab 1 or we won't be able to compile this. It doesn't look like it's going to let me change it, so I'll hit OK. And if I go to files now, it's not added to the project, so I will right click on files and choose add or remove files in the project, and I will hit browse button, and I do have a lab1.v file here, it's just not part of the project, so I will call this lab1 from BDF. And the reason I'm changing the name is because I cannot have two files with the same name, even if they have different extensions, because Quartus treats these as the same. They're a module, they're just a different format. And that. And hit OK. And if I look at lab1 from BDF, I can actually take a look at the Verilog that Quartus generated, and you'll see that this is actually looks like this is a functional implementation that it's used, not structural, but this is the functional implementation that it has decided to go with. And so that might be a good place to get started to kind of understand. I will not accept this as a submission, so you can't just generate this and I will know, but if you wanted as a reference to get syntax, to get an idea of what's happening, perfectly acceptable to do this and figure out kind of what it's doing. All right? Any questions? All right? Awesome. Thanks, you guys. That is everything for the first part of this lab, so I'll let you guys go do what we've just done. If you haven't, try to get it compiled and on your board today if you can.